Arctic news. Extinction. Will humans be extinct by 2026? This page was written mostly in 2016, with some content added later. Above images from a 2021 post. 2016 image. Click on images to enlarge. In the Arctic, vast amounts of carbon are stored in soils that are now still largely frozen. As temperatures continue to rise and soils thaw, much of this carbon will be converted by microbes into carbon dioxide or methane, adding further greenhouse gases to the atmosphere. In addition, vast amounts of methane are stored in sediments under the Arctic Ocean seafloor, in the form of methane hydrates and free gas. As temperatures rise, these sediments from the seafloor. Due to the abrupt character of such releases, and the fact that many seas in the Arctic Ocean are shallow, much of the methane will then enter the atmosphere without getting broken down in the water. What makes the situation so dangerous is that huge eruptions from the seafloor of the Arctic Ocean can happen at any time. We can just count ourselves lucky that it hasn't happened as yet. As temperatures continue to rise, the risk that this will happen keeps growing. This dangerous situation has developed because emissions by people have made the temperature of the water in the Arctic Ocean rise at rates much faster than the rest of the world, due to a number of feedbacks. One such feedback is the retreat of the sea ice, which in turn makes the Arctic Ocean heat up even more, as much sunlight that was previously reflected back into space by the sea ice instead gets absorbed by the water when the sea ice is gone. Without sea ice, storms can also develop more easily. Storms can mix warm surface waters all the way down to the bottom of shallow seas, reaching cracks in sediments filled with ice. This ice has until now acted as a glue, holding the sediment together. As the ice melts, sediments can become destabilized by even small differences in temperature and pressure that can be triggered by earthquakes, undersea landslides, or changes in ocean currents. As a result, huge amounts of methane can erupt from the seafloor of the Arctic Ocean, and once this occurs, it will further raise temperatures, especially over the Arctic, thus acting as another self-reinforcing feedback loop that again makes the situation even worse in the Arctic, with higher temperatures causing even further methane releases, in a vicious cycle leading to runaway global warming. Such a temperature rise in the Arctic will not stay within the borders of the Arctic. It will trigger huge firestorms in forests and peatlands in North America and Russia, adding further emissions including carbon monoxide, ozone, brown carbon, and soot that can settle on mountains, speeding up the melting of glaciers and threatening to stop the flow of rivers that people depend on for their livelihood. As a result, huge amounts of methane can erupt from the seafloor of the Arctic Ocean, and once this occurs, it will further raise temperatures, especially over the Arctic, thus acting as another self-reinforcing feedback loop that again makes the situation even worse in the Arctic, with higher temperatures causing even further methane releases, in a vicious cycle leading to runaway global warming. Such a temperature rise in the Arctic will not stay within the borders of the Arctic. It will trigger huge firestorms in forests and peatlands in North America and Russia, adding further emissions including carbon monoxide, ozone, brown carbon, and soot that can settle on mountains, speeding up the melting of glaciers and threatening to stop the flow of rivers that people depend on for their livelihood. These developments can take place at such a rapid speed that adaptation will be futile. More extreme weather events can hit the same area with a succession of droughts, cold snaps, floods, heat waves, and wildfires that follow each other up rapidly. Within just a few years, the combined impact of extreme weather, falls in soil quality and air quality, habitat loss and shortages of food, water, shelter, and just about all the basic things needed to sustain life can threaten most, if not all life on Earth, with extinction. A global temperature rise of 18.44 degrees Celsius by 2026. How much have temperatures risen, and how much additional rise could eventuate over the next few years? The image on the right shows a potential global temperature rise by 2026 from pre-industrial levels. This rise contains a number of elements, as discussed below from the bottom of the bar up. Pre-industrial to 2020, 2.29 degrees Celsius. The magenta element at the bottom reflects the temperature rise that has already taken place. From 3420 BC, emissions by people have been higher than the amount to negate the natural trend for the temperature to fall, as discussed at the pre-industrial page and as illustrated by the image at the top. Rise due to greenhouse gases added 2020 to 2026, 0.5 degrees Celsius plus 0.35 degrees Celsius. The purple element reflects the rise due to the amount of carbon dioxide and other greenhouse gases added from 2020 to 2026. Greenhouse gas levels in the atmosphere have continued to rise due to high emissions by people and due to feedbacks that are kicking in, such as forest fires and reduced carbon sinks. Furthermore, maximum warming occurs about 1 decade after a carbon dioxide emission, so the full warming wrath of the carbon dioxide emissions over the past decade is still to come. In conclusion, an extra 0.5 degrees Celsius warming by 2026 seems possible from carbon dioxide levels alone. The dark blue element reflects an extra 0.35 degrees Celsius that could be caused by additional methane, nitrous oxide, and other greenhouse gases emitted between 2020 and 2026. This dark blue element is discussed further below. Loss of the sulfate cooling effect, 1.9 degrees Celsius, and rise due to other aerosols and gases, 0.6 degrees Celsius. With dramatic cuts in emissions, there will also be a dramatic fall in aerosols that currently mask the full warming of greenhouse gases. From 1850 to 2010, anthropogenic aerosols brought about a decrease of tilde-operator 2.53 K, according to this study. While not all of the aerosol's masking effect may fall away over the next few years, much of it could, in case of industrial collapse. A 1.9 degrees Celsius temperature rise due to loss of sulfate cooling therefore seems possible by the year 2026. Furthermore, the temperature could rise due to additional biomass burning and forest fires, causing emissions of further aerosols such as brown carbon and soot, and gases such as carbon monoxide and nitrogen oxides, as discussed in this post. Snow and ice demise in the Arctic, jet stream changes, and associated changes, 1.6 degrees Celsius. Warming due to Arctic snow and ice decline, i.e. of both sea ice and the snow and ice cover on land, may well exceed 2.6 W/m superscript 2, calculated Professor Peter Wadhams in 2012. This could more than double the current net global warming caused by people since pre-industrial times. Associated changes include the loss of the ice buffer, latent heat, greater heat transfer into the Arctic Ocean due to stronger winds, and the resulting freshwater lid on the North Atlantic, and more heat entering the atmosphere from the Arctic Ocean due to more open water in the Arctic Ocean. A 1.6 degrees Celsius warming due to albedo changes and associated changes seems possible over the next few years, as discussed in this post. Methane eruptions from the seafloor, 1.1 degrees Celsius. Dr. Natalia Shakova et al. Wrote in a paper presented at EGU General Assembly 2008 that we consider release of up to 50 GT of predicted amount of hydrate storage as highly possible for abrupt release at any time. Authors calculated that such a release would cause 1.3 degrees Celsius warming by 2100. This 1.3 degrees Celsius warming, by 2100, from an extra 50 GT of methane seems conservative when considering that there now is only some 5 GT of methane in the atmosphere, and over the next 10 years this 5 GT is already responsible for more warming than all the carbon dioxide emitted by people since the start of the Industrial Revolution. Professor Peter Wadhams co-authored a study that calculated that methane release from the seafloor of the Arctic Ocean could yield 0.6 degrees Celsius warming of the planet in 5 years. See video at earlier post. In conclusion, as temperatures keep rising, a 1.1 degrees Celsius warming due to methane releases from sediments at the seafloor of the world's ocean seems well possible over the next few years, and even more temperature rise seems possible beyond that, as also discussed in this post. Extra water vapor feedback, 2.1 degrees Celsius. Rising temperatures will result in more water vapor in the atmosphere, 7% more water vapor for every 1 degree Celsius warming, further amplifying the temperature rise, since water vapor is a potent greenhouse gas. Extra water vapor will result from warming due to the changes in the Arctic, and due to methane releases from the seafloor that could strike within years, and could result in huge warming in addition to the warming that is already there now. The IPCC says, water vapor feedback acting alone approximately doubles the warming from what it would be for fixed water vapor. Furthermore, water vapor feedback acts to amplify other feedbacks in models, such as cloud feedback and ice albedo feedback. If cloud feedback is strongly positive, the water vapor feedback can lead to 3.5 times as much warming as would be the case if water vapor concentration were held fixed. The temperature rise due to extra water vapor works immediately, i.e. it goes hand in hand with rises due to other warming elements. Research indicates that, if the temperature of Earth rises by 1 degree Celsius, the associated increase in water vapor will trap an extra 2 watts of energy per m superscript 2. give it a possible additional warming of 2.7 degrees Celsius due to just two elements, i.e. snow, ice, wind and ocean changes, such as Arctic albedo changes, and seafloor methane, an additional warming over the next few years of 2.1 degrees Celsius due to extra water vapor in the atmosphere therefore does seem well possible over the next few years. Further contributors to temperature rise, continued from above, besides further gases and aerosols emitted between 2020 and 2026, additional rise in temperature could eventuate due to feedbacks and interactions between the above elements. Changes to the atmosphere, clouds, storms, lightning, etc. Additional water vapor in the atmosphere and extra energy trapped in the atmosphere will result in more intense storms and precipitation, flooding and lightning. Flooding can cause rapid decomposition of vegetation, resulting in strong methane releases. Furthermore, plumes above the anvil clouds of severe storms can bring water vapor up to high altitudes, into the stratosphere, threatening to cause depletion of stratospheric ozone and contribute to the formation of cirrus clouds that trap a lot of heat that would otherwise be radiated away from Earth into space. Stronger storms also threaten to cause more lightning. The number of lightning strikes can be expected to increase by about 12% for every 1 degree Celsius of rise in global average air temperature. At 3 to 8 miles height, during the summer months, lightning activity increases NOx by as much as 90% and tropospheric ozone by more than 30%. From an earlier post, the combination of higher temperatures and more lightning will also cause more wildfires, resulting in additional emissions of carbon dioxide, black carbon, brown carbon, methane and carbon monoxide. Tropospheric ozone has a direct warming impact as a greenhouse gas, while carbon monoxide can indirectly cause warming by extending the lifetime of methane. The worst wildfires can send smoke high enough to affect the ozone layer in the stratosphere. Damage to the ozone layer and climate change are forming a dangerous feedback loop. Changes to soils and ecosystems on land. Additional warming of the atmosphere can also take place when sinks that are currently holding back warming instead turn into sources. An increase in the uptake of carbon by vegetation until now was attributed in a recent study to higher CO2 levels in the atmosphere. This land sink now appears to turn into a source of carbon emissions due to deforestation and soil degradation caused by agricultural practices and more extreme weather, as discussed in this post. Changes to the cryosphere, global sea ice, snow and ice cover on land, glaciers, etc. From sea ice is shrinking for years. Global warming was also thought to be held back by growth of sea ice around Antarctica and the greater albedo resulting from that. Recently, however, sea ice around Antarctica reached record low extent for the time of the year, late 2016. On November 23, 2016, Antarctic sea ice extent was 2.615 million square kilometers smaller than it was on November 23, 2015. To put this 2.615 million square kilometers in perspective, the minimum Arctic sea ice in 2012 was 3.387 million square kilometers, for 0.157 less than the minimum extent in 1980, as illustrated by the image on the right. Ever warmer oceans and stronger winds that move sea ice away from Antarctica make the outlook for global sea ice grim. Furthermore, higher temperatures look set to cause more growth of algae and melting, resulting in further albedo decline. Higher temperatures on land will cause warmer water from rivers to enter the Arctic Ocean. Higher temperatures on land will also trigger more wildfires, resulting in emissions such as a black carbon that can settle on the snow and ice cover in the Arctic. A recently published study warns that permafrost loss is likely to be 4 million square kilometers, about 1.5 million square miles, for each 1 degree Celsius 1.8 degrees Fahrenheit temperature rise. This is a self-reinforcing feedback loop, since the albedo loss will further speed up warming in the Arctic, which will also cause more emissions of carbon dioxide, nitrous oxide and methane. Image from 10 degrees Celsius or 18 degrees Fahrenheit warmer by 2021. Changes to oceans. Warmer water tends to form a layer at the surface that does not mix well with the water underneath, as discussed in an earlier post and confirmed in a more recent study. Stratification reduces the capability of oceans to take up heat from the atmosphere, thus speeding up warming of the atmosphere. Until now, oceans have been taking up 93.4% of the extra heat that is caused by emissions by people. So, even a small decrease in the amount of heat that oceans now take out of the atmosphere would leave much more heat in the atmosphere, thus resulting in a dramatic rise of global air temperatures. Additionally, Greater stratification of oceans results in less growth of phytoplankton, and thus in less take-up of carbon dioxide in oceans. So more carbon dioxide remains in the atmosphere. Furthermore, lower oxygen levels at the top layer of oceans can also increase releases of nitrous oxide. Finally, heating up of oceans increases the danger of eruptions of methane from the seafloor, as discussed above. More greenhouse gases in the atmosphere means that less heat can leave Earth, as it gets trapped by these greenhouse gases. So this is another self-reinforcing feedback loop that further heats up the air, the cryosphere and oceans, as described under Feedback 29. In conclusion, the temperature rise is causing oceans to change, resulting in a rise in greenhouse gas levels, and in more heat remaining in the atmosphere. This could dramatically drive up air temperatures in the lower troposphere, resulting in runaway global warming. The joint impact from such changes may well amount to an additional 0.35 degrees Celsius warming for further feedbacks over the next few years, or much more than that over more years, canceling out possible overestimations in other elements. Clouds feedback, 8 degrees Celsius. Disappearance of stratocumulus clouds could make the temperatures go up strongly and rather abruptly. By the time CO2e levels will have risen to the cloud's tipping point of 1,200 ppm CO2e, temperatures will already have gone up a lot in line with the warming from rising CO2e levels. On top of this, the cloud's feedback itself will then trigger an additional surface warming of some 8 degrees Celsius globally, as discussed at the cloud's feedback page and an earlier post. Summary. Total global temperature rise could be as much as 18.44 degrees Celsius by 2026 in summary. Adding up all the warming associated with the above elements results in a total potential global temperature rise, land and ocean, of more than 18.44 degrees Celsius in a matter of years, by as early as 2026. Accordingly, this could lead to numbers of climate-related global deaths much in line with the 2016 prognosis below, which was an update of this 2014 prognosis. Click on images to enlarge. The situation is dire and calls for comprehensive and effective action as described in the climate plan. Further reading on specific warming elements and further topics. Pre-industrial to 2020, 2.29 degrees Celsius. How much warming have humans caused?